Okay, we should get started. Good morning. Well, because of our little storm and class canceled, I just kind of moved everything back. And so your assignment is not due today. Um, it will be, we should have it ready to go on Monday. I needed extra time to show you some more problem examples. That's what we really need to do a lot of today. What was the other thing? Well, then obviously the test is, everything's backed up. So instead of having the test on Monday like I was planning, so the idea is today we'll do some problems. We'll see if we want to do that the whole period, or maybe we want to start reviewing a little bit. Monday we'll review the 3 chapters. Wednesday will be our first test. The only reason I have this up here is I think this is the last problem we did. I know, did we do that Gerald, Eleanor, SAT, ACT problem?
Yeah, only there was 3.7. Problem 3.7. For example, something about height.
Did we do this one?
That's the last.
Okay. So then let's start here. Okay. This is a very important problem because it shows I had made a claim at one time that the standard deviation allows you to cross over totally different scales. This problem is a perfect example of that. It's example 3A. I got it all done, but that's okay. It says Eleanor scores 680 on the math part of the SAT. A little later it says Gerald got a 27 on the math ACT. Well, 680 sure sounds a lot better than 27. Well, they're on totally different scales, right? So the question is, who did better? And the way to find out is standardize them. And so do you notice I broke this into 2 separate problems. I took Eleanor and I set up her z-score. Her score of 680 minus, and this is all in the problem. I've got it on the right there. The standard deviation, 680 minus the standard deviation of 516 divided by the standard deviation of 114. And that all comes out to 1.44. Okay, now let me just stop. What does that mean? It means on a normal curve, she is 1.44 notches to the right of the mean. You know what I mean by notches, standard deviation. Okay. Gerald, here we got to use this data because this is the SAT data. Gerald, I take his score, subtract the mean for that test, divide by the standard deviation for that test, and here I get 1.28. So Gerald is 1.28 notches to the right. That tells me that Eleanor did better. So even though, why? Because this standard score is higher than that one. Eleanor is farther to the right of the mean than Gerald is. And so even though they have totally different scales, I now can compare them. And this is what's really cool about standardizing and standard deviation. You can take totally different things and actually make a comparison. So I got it covered up on the bottom, but the obvious result is that in this case, Eleanor did better because she has the higher standard score. So that, boy, that's a huge thing, and that's a really important thing. So the standardizing, now I didn't. By the way, I did nothing with percents here, right? But I didn't have to. All I have to know to compare the two is to find out that one is further to the right than the other on the standard scale. Okay. I don't know if you had enough time with that, but I'm going to move on to another one. Here's an example in the book. And you know, maybe I should go ahead and we'll come back. If you haven't noticed it already, there's a new notation in this chapter. That's where they use a capital N, parentheses, and then they have two numbers in there. This means, whenever you see that, this means that this is a normal distribution. That's what the N stands for. And the first number in here is always the mean, and the second number in parentheses is always standard deviation. So if you tell me, hey, it's a normal curve, one of those nice symmetrical guys, and here's where the middle is, and here's how long each notch is, you've told the person everything about everything they need to know. So when you see this notation, and you're going to see it in your assignments, you're going to see it throughout the chapter, where you have an N, parentheses, they're actually telling you it's a normal distribution, and we're going to tell you what the mean is, and we're going to tell you what the standard deviation is. Okay, so I don't think I made that point to you. I don't remember if I did or not, but you're going to start seeing that, and you're going to go, whoa, what's this N stuff with an ordered pair in it? That's what it means. Okay, so now, you notice I have a problem like this shown. Look at way up in the top right. I've got an N with a normal distribution with a mean of 64 and a standard deviation of 2.7. And in this particular example on page 67, the question is, what proportion of young women are less than 70 inches tall? Now, if I did this problem with you, let me know. My two sections are just slightly out of sync. Okay, so I don't care if you say we already did that. Did we? We came up with, did we do that? We came up with 98.68%? Okay. You said we didn't, and others say we did.
We did 3.3, 3.5, 3.7.
But not 3.4?
No.
Well, I'm going to do it. For those of you who have already seen it, my deep apologies. Okay, here we go. Question is, what percent of all women are below 70 inches tall, given the data on the top right? So you notice I wrote down, oh, okay, this is what they gave me. Now they want to know about this score, 70. So good old Z, you pull it out, calculate the standard score. Okay, in this case, I didn't write the numbers down, but what would they be? 70 minus 64 divided by 2.7. I didn't write it out, but that would go right in here. And when I did that arithmetic, I came up with 2.22. Okay, now it's our standard score, but the book wanted to know the percent that's less than that. That's good news, because remember, the table in the front of the book will give you always less. So, pick up your book, open it up, and look for a Z-score of 2.22. So you look for the Z's along the left. You're not going to use this side, because this is all negatives. This is a positive 2.22. Remember, that means to the right. If you were negatives, that means we're over on the left side. So positive 2.22. Everybody knows how to do that. You have to go to the 2.2 row and move over to the 0.02 column. And does everybody see 0.9868 there? Okay, so that's it. That's what percent. Now, of course, all I did is change that to a percent by moving the decimal 2 places to the right. So what percent of women are below 70 inches tall? That's a very high percentage. Why is that? Because the mean of women is 64 in this group. So this is quite a bit above the mean. Everybody should spot that. And so we're already in kind of rarefied territory. So what percentage are less than that? Almost all of them. 98.68%. So there's another example of using table A. Okay. Have we done this one? 320? I don't think we have. Okay, let's do this one next. This is on page 75. By the way, I also have it set up in a few seconds here, maybe the next one, I can't quite remember. I'm going to do some of the exercises too. But anyway, oh, this is an exercise. Duh. Wake up. Okay. I don't know, I've been here early today too. I just mentally not clicking. So on this exercise, NCAA rules for athletes. National Collegiate Athletic Association requires Division I athletes to score at least 820 on the combined math verbal parts of the SAT in order to compete in their first college year. Higher scores are required for students with poor high school grades. In 2002, the scores for 1.3 million students taking the SATs were approximately normal, with a mean of 1020, which I wrote up there, and a standard deviation of 207, which I wrote up there. What percent of all students had scores less than 820? See, now this is important because we're finding out what percent of students were not able to play because of being ineligible by the NCAA rules. Okay, so there's our score. Let's do it. We need to find the z-score. So z equals x minus mu over sigma. And in this case, x is 820. Mu is 1020. And standard deviation is 207. So what is that? Negative 200 on the top? And on the bottom, 207. So this is going to be what? Like negative 0.9 something? Let's quick calculate, get it more precise. So we got 200 divided by 207. Yeah, negative 0.966. By the way, negative. What does negative tell you again? That the score we're checking out is somewhere to the left of the middle point. A little bit below average. Okay. Well, in fact, it's almost what? Negative 0.96, wouldn't you agree, is probably about in here? It's not quite negative 1. You can just visualize that. Okay. Now, let's look it up. What's the percent? So now, what does that really mean? Negative 0.97? Negative 0.97. What do you get? Looking it up in your table, you get 0.1660. What is that percent-wise? Percent-wise? 16.6%. So, I mean, the bottom line is for this question, that means 16.6% of the people that wanted to participate were ineligible just by the NCAA rules. And of course, if you're in the NCAA, you have to abide by those rules. And because we are in the NCAA, we have to abide by those rules. So anyway, interesting. I'm sure they all, by the way, this gave the SAT. I'm sure they have an ACT equivalent. I just don't know what it is. All right. Anybody have a question about exercise 20? Let's do number 22. Not very far away. I guess I'm going to erase what we have here and we'll just reconstruct. Okay, 22 says, heights of men and women. The heights of men aged 20 to 29 follow this normal, see there's that notation. It's a normal distribution with a mean of 64. That's the women, excuse me. The heights of women. Normal, 64 for a mean standard deviation of 2.7. Men the same age have heights distributed as normal with a mean of 69.3 and a standard deviation of 2.8. This is a little bit tricky. It says, what percentage of young men are shorter than the mean height of young women? So in other words, what percentage of the male population are actually below the women average?
3.2 to 3.2.
Am I reading the wrong one?
It just says what percentage of young women are
Oh, I did it the wrong. I started reading 23. What percentage of young women are taller than the average of men? Okay. Well, what is the average of men? 69.3. So how many women are above that is the big question, right? Okay, so what percentage, and you notice, where did I get this? I just said, oh, okay, so we want to use the score of 69.3. Why? Because that's the average of the men. So what percentage? We actually know, let me think about this. Oh, so we got to work backwards. We know the percent. Take your table. Now we got to find 69.3 in the table. So where's, in other words, where's .6930 in the table? This is a little different search. You got to look in the body. 6930, as close as you can get it. Looks to me like it's as close as we can get it. It's .051. I'm sorry, 0.51. No? You guys don't quite see what I'm doing. Okay. Most of you do. But anyway, you're looking in the table and you're trying to find something as close as possible to .6930. Well, the closest one I got is .6950.
Why would you do .6915?
They're equidistant, I guess. Either one. Actually, it's exactly halfway between them. But what are you not seeing? Tell me.
So what we're looking at 69.3.
Yeah, I shouldn't have called that X.
So
What am I doing? Wait a minute. What am I?
It's closer to 15 now.
Hang on, I'm doing this wrong. I want to know what percent of women's scores. Yeah. So I'm sorry, that's not a percent. That's a height. I apologize. No wonder you're confused. Okay, take the Z. We know X is 69.3. Subtract the mean, 64. Divide by the standard deviation of 2.7. And slur there, sorry. Thanks for giving me that strange look. That's what clued me. I needed that. Okay, 69 point, this is 2.7 down here. Okay, now what do we get on top? 5.3? And put that over 2.7, and boy, that's almost 2, isn't it? That's like 1.9-ish. Okay, let's check it out. 5.3 divided by 2.7. Yeah, 1.96. Okay, and make sure I got the question right. I lost the page now. I love that. Thank you. One thing about the table. What percent of young women are notice? Taller. Taller. Uh-oh. The table always gives us less. So just so you know, we're going to have to make an adjustment there. So first of all, what percentage of women are below this? Well, let's look it up. 1.96 for a z-score. 1.96. And I get, what, 0.9750? But that's the percentage below. And the question said, what percentage of women are taller? So I have to subtract from 1. And of course, what's going to happen here? They're all going to be 10s. That's a 5. That's a 3. That's supposed to be a 2. Right? And now when you change that to a percent, what do you get? Now, let's see if that makes sense. What percentage of women are taller than the average of men? Is that supposed to be a tiny number? Yeah, that's going to be a tiny number. That makes sense that it's so low. Okay, there's another one of those. All right, I kind of ran out now, but you guys have probably started working on your assignments. Do you want to pick out some that maybe you struggled with a little bit on the odds, and maybe we could do a couple of those? Austin?
You go number
19? Sure. Okay, 319. Standard normal drill. Find the number z such that the proportion of observations that are less than z in a standard normal distribution is 0.8. Okay. So, they're already giving us the percent, right? It's 80%. So what z will give you 80% below it? So we got to do a backwards table reading. And where do you find 80% in the table? So here you got to try to find 0.80 or something as close as possible. 0.8000. Closest one is what? 0.7995? You with me, Austin? Okay. Once you got that number, what's the z for that? So now you got to read back to the left of the top. What's the z that'll give you 0.7995? Isn't it 0.84?
Oh, yeah, I know you're asking.
Okay, so you're with me on this? So that one is what? 0.84? Let's just write that down. I never did make a page for you here. Okay, so this is number 19. 3.19. And we just found for part A, I don't think I need to show you any more work because it was just a regular reverse table. But now, what's part B? Part B says find the number z such that 35% are greater. Okay, let's stop and think. The table won't give me greater. The table always gives me less. So if we want to know when 35% are greater, what percentage would be less? 65. So really, we want to look for 65, right? Does that make sense? Because the table only gives us less. So now, look in your table and try to find 0.6500 as close as you can. 0.6500. Well, it's what, a little bit closer to, what do you get? 0.39? It's a little closer to 9 than 8, isn't it? 0.39. 0.39. And that's the end of that one. So those are both reverse table lookups, but the one B was a little tricky because they asked you a greater. And remember, your table always gives you less. So you gotta have your head on straight when you do these. And whoa, do I? Yeah, that's right. If there's 35% greater, then there must be 65% less. You know. Another one. Yes. 3.11. Okay. Now let's just start over. I got about 12 pages on 11 here, and All right, 3.11. We got a lot of parts to this, don't we? How hard do locomotives pull? An important measure of performance of a locomotive is its adhesion, which is the locomotive's pulling force is a multiple of its weight. The adhesion of one 4,400 horsepower diesel locomotive model varies in actual use according to a normal distribution. By the way, they really do. You're just starting to see the unbelievable huge number of things that follow the normal distribution curve. Anyway, mean 0.37. Let's get that down. And the standard deviation 0.4, 0.04. Okay, part A. What proportion of adhesions measured in use are higher than 0.40? So this time they're telling you this. First of all, let's get this down. There's our score. And notice the key word, higher. Uh-oh. Remember, table will only give you less. So we just got to remember that. Let's standardize it first. Score minus mean divided by standard deviation. Well, this one we don't need a calculator for. That comes out exactly to 0.75. Okay, so now we got the z-score. And the z-score, we could go to the table, but wait a minute. Before we go to the table, remember, the table will give us less, and they want to know more. So after we get our less answer, we're going to have to subtract it from 1. So first of all, what's our percent? 0.75. Do you get 0.7734? Okay, let's write that down. But we don't want less, we want greater, so we have to do this subtraction thing. So, and usually they want you to round it off to the 10th. So final answer for A looks like it's 23.8%. So let's just back to our question here. Make sure what we have makes sense. Sorry, I'm trying to find my way back to the problem. What percentage of adhesions measured in use are higher than 0.40? Okay, not a lot. About 24%. Is it? What should it be? Forgot to do my borrowing, didn't I? Thank you. Sorry about that. Let's just do it. So yeah, so they're all 9s except for the last one. So this should be a 6, this should be a 6, this should be a 2, and this should be a 2. So 22.7%. Thank you. Sorry about that. Part B. What's part B? What proportion of adhesion? Oh, okay, this is a good one too. All right. I don't know if I have room here, but we'll make it work. Okay, so this time we have 2 scores. We have score 1, which is 0.40, which we've already done. Please note, we did it in the previous problem. And we have score 2, which is 0.50. Now, remember, how do you do these betweeners? The idea is find both numbers and subtract the smaller from the larger, and that'll give you the part between. Well, we've already found one, so we don't need to do that again. So let's do the other one. Now, only other thing I'll say here too is, because we don't care if it's below or above, actually I could use, I don't need to even subtract from 1. Because all we want to know is what's between. So I could have actually, now I can make use of this 0.7734 directly. So let me just write that down. This one is actually less, 0.7734. We got to do the part for 50 now. Okay? So, z equals x minus mu over sigma. And in this case, x is 0.50. Subtract the mean, which is 137. Divide by the standard deviation, which is 0.04. So what's that, 0.13 over 0.04, which is 3 is 12, and that's 3 1/4, isn't it? 3, because 4 times 3 is 12, 1. Yep, it's 3.25. Okay, now look it up in the table. Z-score, well, this is a big one, 3.25, and I get 0.9994. Let's put that up here. And now I can subtract x1 from x2. Point 7734, nothing, 622. Well, isn't that interesting? It's the same answer we got for part A, just by accident. Weird. That was the amount less of the first number, and that's also the amount between these two. Somebody got the answer, Sandy? Just check, is that correct? Isn't that interesting? But just so you know, that's totally a freak accident. Well, I mean, they might have designed it that way, but normally, please note, that's not going to go like that. Is that it for 11? No, there's one more part. I don't know if we have time to do this one, but let's just talk about it. Part C. Improvements in the locomotive's computer controls change. Oh, okay. It changes the distribution, and this time the mean changes and the standard deviation changes. Go back and do A and B over again with these new numbers. So I don't know if we need to do it. It's the same problem again, only this time use the new standard deviation and the new sigma. So it's what's that? I'm not saying you should go, oh, well, that's no big deal, it's the same, so therefore I'm not going to do it. I'm just saying to try to utilize it in class time. I don't know if I really need to do it again unless somebody wants me to. It's the same problem. Yeah.
Instead of showing the word twice, we just like substitute numbers.
Well, when you say show the work, you mean like this?
It's supposed to be a little bit different, but
I would, honestly, I'd write the work out. If you call, are you calling this work? That doesn't take long. I would say, I wouldn't, you do that up here, you're asking for trouble anyway. Well, I know what you're probably thinking is you can do it, not write it on paper and compare it to the back, and if it agrees, you know that's true, but I really wouldn't want to do less than this. So I think there I'd have no choice but to write it over. Yeah. Oh. Karis first? 13?
I got a question.
Okay, then go ahead.
Item C, and with 0.5 from B to minus that 0.41 divided by 0.7B at 4.5, that's not on our neighborhood.
It's not on what?
Our little sheet of paper, find a number, it doesn't walk that high.
Oh, okay, yeah. Thank you. What happens when you get a number that's either below negative, a z-score below negative 3.4, or above positive 3.4. All right, if you're above positive 3.4, well, look at the last line of the table, above 3.4. You notice how it's already at 99.98%? If you get anything above that, you can assume it's 100. And if you get anything below this, you can assume it's goose egg, 0. So if you're off the table, just remember, if you're off this way, just call it 100%. If you're off this way, just call it 0. I'm glad you brought that up. Thanks. Yeah, if you're off the table, that's what you do. Okay, now we're on to, what was it, 313? 313. IQ scores. Yeah. Okay. New page. Scores on the Wechsler Adult Intelligence Scale are approximately normal, with mu 100 and sigma 15. All right, going on. What IQ scores fall in the lowest 25% of the distribution? Okay, so A, lowest 25%. Below what score? That's basically the question. So here's one where they've given you the percent, and the first thing you got to do is you're going to find a z-score. So here's where we got to read the table backwards again. And the good news is this is lowest. In other words, below, so we're in the right realm here. Try to find something as close to 0.2500 as you can. Looks like, what, 0.2483 is about as good as we're going to do? No. Yeah. That's 17 away. And the next, no, 2514 is better. That's only 14 away. What's the z-score for that? Negative 0.67? Okay, so z equals negative 0.67. Now, take your standard score formula. Okay, now what do we know? We know z. Cool. Negative 0.67. We don't know x. That's what we're looking for. We do know mu. And we do know sigma. So do you see how we're only missing one thing, but it's not in the normal position you're expecting it to be in? So what's step one? Multiply. You got to do a little algebra here. So we got to get 15 and multiply both sides by 15. By the way, this is really just negative 2/3, isn't it? Here. What's negative 2/3 times 15? Negative 10, right? 3 goes to 5. Negative 10. Add 100 to both sides. There it is. Below what score are 25? Excuse me. Yeah. Below what score are 25% of the IQs? Answer: 90. So that's the answer to part A. Anybody need clarification on part A before I move over to part B? I'm going to make a new page because it's too crowded. Okay, so 313 part B. Let me just repeat this. Okay, on part B, what are they saying? How high an IQ score is needed to be in the top 5%? So again, we're looking for a score. We don't know. That's what you're trying to find. But you do know you're in the top 5%. Now, top 5% means above. If 5% are above a score, what percent would be below the score? 95. Okay, so now look in your table for as close as you can get to 0.9500. And it's right between two, isn't it? Right between 1.64 and 1.65. So I would write Z is equal to you follow that? It's halfway between 1.64 and 1.65. Isn't it halfway between that? 1.645? Okay. So now, same problem before. Use your standard score formula. Plug in what you know. We know Z. We don't know X. We do know mu. We do know sigma. So now we got to do some algebra. Multiply both sides by 15. So I'll pull out my calculator for this. So what's 15 times 1.645? And it's 24.675. And now, add 100 to both sides, and you got it. So what score do you have to only have 5% of the people above you? You would have to have a 125 on the IQ test. Because I don't think they give decimal IQs, do they? No. I think they just give you whole numbers. So, and I can't say 124 because that's a hair too low, so I just say 125. Okay, so those are good examples again because we had to do the backwards thing. We had to we start with the table and kind of look out to find Z instead of the normal technique. Well, okay. Well, we got 5 minutes left. So what we're going to do then on Monday, we will devote entirely to reviewing chapters 1, 2, and 3. Now, I guess you could say we've done a pretty thorough job of reviewing chapter 3. So it's up to you. We can do more of these. But what you really maybe want to concentrate on for Monday is the stuff from the past, chapters 1 and 2. There's not going to be a computer skills test this time. And the other comment is, you notice there's a couple things you can do on a computer for chapter 3, but they're not really shortcuts. They allow you to avoid using the table. So anyway, you can just do your whole assignment you don't have to hand in computer sheets this time. Okay? So ready to go? Anybody? I guess we do have a little time. So I don't know if I can do a whole problem, but other questions you want to bring up? Doesn't look that way. I'll see you on Monday. Have a good weekend.